just wait for that to happen. It's working on it. Yep. Great. So here's our plan for today. We're going to, as the SKCD dictates, we're going to talk about linear regression. And we're going to do a deeper dive here. Basically, we're going to deal with the uncertainty that we put on the weight priors and on the predictive distributions. Right. So before that, let's look at some announcements or logistics of the class. This will also be posted on Piazza. Basically, a reminder that next Monday, 8th of March, is Canberra Day. There's no workshop session that day, and we won't have a makeup workshop section for that either. As a result, so we're going to compress a little bit of linear classification and neural network content into the next 3 lectures. Basically, next Friday, basically what I wrote here is Friday of week 3 plus Monday and Friday of week 4. Right. And after that, we will be mostly catching up, we'll be essentially caught up to the original plan of the class as of last year, which is not itself a goal. And then in order to do this, I have made some choices. So I won't hold you responsible for the derivation of Fisher discriminant. We'll just briefly talk about it. We wouldn't talk about Laplace approximation and Bayesian logistic regression or Bayesian view of classification in detail. So, and another announcement is that there has been some discussion about assignment submission format. So for assignment 1, there is a theory part and programming part. For the theory part, you are encouraged to typeset your solution with LaTeX or your favorite typesetting tool. We believe this is a nice skill to have, especially if you're going to go deeper in AI and machine learning. We liken this to having the skills of doing source control in like introductory computer science classes. But if you have already handwritten the solution or strongly prefer to handwrite your solution, just do it very clearly and take a clear picture with high resolution, high contrast, and then upload to Grayscope and label it with every sub-question as Grayscope instructs you to. So if tutors can't read your solution, I guess you will suffer. So that's the short message. So put the admin aside. So here is what we're going to cover. So far, we have talked about linear regression or linear models of regression. We talked about basis functions, maximum likelihood, regularization on top of maximum likelihood. And then we talked about this bias variance decomposition, which gives us a nice view of what the error and the trade-off between model complexity, variance and bias, and so on. So today we're going to go one step further. So I expect this particular workshop to last for about an hour, and hopefully, like we should be able to get done in an hour and 10 minutes, but let's see. So the reason I say that is there is not a lot of content, but it's rather technical. It is, I would say, more technical than many other lectures, but I think there is a good reason for this. One reason is that this, so we're mainly going to look at Bayesian regression. This is the main goal for today. And in order to look at this, we're going to look at a bunch of essentially prerequisites or steps to get there. So conjugate prior, conditional of Gaussian variables, and so on. So comparing to the lecture videos and slides from last year, we are expanding this part in more detail to give you, I guess, a detailed view of what this involves. The benefit of this are twofold. I would say the meta goal is one, understand conjugate priors. This will help you in assignment 1. theory part. The second meta goal is to like get a little more comfortable in manipulating Gaussian distributions, right? So Gaussians are very important distributions, as we covered last week. So basically the quadratic form and manipulating it. So if you are going any further in machine learning beyond this class, you'll find this very helpful, like Gaussian processes and other Bayesian versions, VAE even. So yes, so that's I guess the main goal. And then there are, I would say, the predictive distributions is another nice byproduct of a Bayesian view of models that we should cover. And then at the end, we aim to cover another nice mathematical results that tells you the underlying reason behind curse of dimensionality, especially for Gaussian variables. So it's quite counterintuitive. But I saw it's nice to have. So let me state basically the goal of this main section, and then we will unfold it over about a dozen or so slides. So equation 3.10, so this was known to you, like last workshop, right? Last session. Basically, the distribution or likelihood function of observing a bunch of training targets given the input and weights is the product of Gaussians, where the mean is determined by this linear function of weights and the basis function vector, and the variance is this noise parameter beta, or noise precision beta. Right, the variance is beta inverse, right? So what is new for this this particular session is this is the prior distribution of W. Now we introduce some prior belief of the weight W. Remember, all the way from week 1, we kind of said we don't want W to be too big, right? If the magnitude of W is too big, then going outside of the observed range of X, if we're doing polynomial regressions, then the value of the target function will blow up. So we now state this more formally with a mean M0 and the variance S0, or like covariance vector, because W is a vector, so we state this more formally, right? So M is a vector, this is S0 is about D by D, like D is the input dimension, right? And we claim that the posterior distribution of the weight vector W given a set of observed training targets is also a Gaussian distribution, right? So this is a claim so far. We can verify this, right? Where we denote that after observing n data points, number of data points, the expression of M, like the posterior mean and covariance matrix, is as follows. So this was simply stated in the book, in a contiguous chunk. And also in last year's slides, the derivation started pretty much from the last step. So in the next 20 minutes, we're going to basically get there via 3 stepping stones. First, we'll take a look at conjugate prior, then we look at Gaussian distributions in detail, right? So conjugate prior is basically a class of prior probability distributions of, let's say, weights, so that the likelihood function and the posterior distribution are in the same family as the weights. So to be more precise, right? So if the likelihood function is, let's say, multivariate normal, this is our case here, then the prior is said to be conjugate to that if the posterior is also the same form as the prior, right? Of P of W given T or given X, right? So it should be the same, right, as this one. So in the homework or assignment 1, you are going to basically look at mainly the binomial, but also covers the Bernoulli, this case. And in the next while, we're going to look at Gaussians. So like the prior is conjugate to the likelihood function, which is multivariate normal. And in here, the conjugate class of distribution we claim is also a Gaussian distribution, right? And then there are, so this slides also gives essentially a menu of popular choice of distributions. For example, if we have words, which are sort of this set of discrete choices, then the likelihood function is multinomial. For example, if we have bag of words, then the conjugate prior to that is Dirichlet distribution, so-called Dirichlet. So it's sort of a distribution of multinomials. There's a whole book section about this. We're not going to cover it in this class. But if you're interested in natural language processing, this is sort of the underlying mechanism behind what's called latent Dirichlet analysis. It's quite a nice framework, right? So that's basically a definition of conjugate priors. The next stepping stone is let's manipulate multivariate Gaussian distributions by looking at basically if our Gaussian has two paths. So the overall direction is that now we have W as a vector and T, the observed set of training targets, and behind this phi, the basis function and other parameters. We would want to, the general direction is that we would want to reason about P of W given T, right? This is the posterior we ultimately want to get. So the intuition is that these are sort of Gaussian variables, and then what's one Gaussian condition on another joining Gaussian variables. If you remember from probability and statistics, if you don't worry, refresh your memory. Basically, if W and T are jointly Gaussian, then they are marginal distributions, and the conditional distributions are also Gaussian. So more formally, so this is in the book. This is going back to section 2.3, I believe. So basically going back to chapter 2, and they use a different notation. So now assume we have the distribution over a one long vector X, and it's partitioned into two parts, XA and XB, right? The overall distribution X is Gaussian. We denote the covariance matrix as sigma. And then the precision matrix, remember in multivariate Gaussians, actually the covariance matrix only appears in a PDF expression as its inverse, or 1 over its determinant, which is also inverse. So denote the precision matrix, which is often convenient to work with as capital gamma, right? So we know that both sigma and gamma are symmetric matrices. This is useful. And then there are also PSD, or positive semi-definite. What does this mean for symmetric matrices? Or it means that all of the eigen values of these matrices are greater or equal to 0. So the geometric intuition of this is, remember last week Friday we talked about multivariate Gaussians having contours like this, right, in the, let's say, x1 and x2 space. So you could formally prove that they are positive semi-definite. I leave that to you. But the geometric intuition is that in this high dimensions, this ellipses or like elliptical spheres are they have non-negative lengths of the axes, which is quite intuitive, right? So we can't have a ellipse with a negative like major and minor axes. So that's an intuition. So now we partition X into two parts, and the corresponding mean vector are also simply partitioned into two parts, right? It's the mean of the first part and the mean of the second part. We can also basically partition the corresponding covariance and precision matrix into the parts. In here, partitioning just means like we have a big matrix, and then A and B may have different dimensionality. For example, W is, let's say, a D by 1 vector, and then T is an N by 1 vector. So then this partition will be first D elements, followed by the next N elements, and so on, right? So if this is the covariance matrix, then sigma A and A will be there, will be on the upper left-hand corner. So and the precision matrix, despite it has different expressions, the size of the partition is the same, right? So let's first think about marginal distributions given the joint distribution. So again, recall, so this part I'm going to skip the proof. There's a whole book section about it. If you're interested, you can read it. I would just simply invoke conclusions from a probability and stats class to say that if two variables are jointly Gaussian, then the marginal distribution is also Gaussian. It's easy to show or intuitive to think about basically if we marginalize over the second part of the variable xb, then xa will have its own mean and covariance matrix that were not affected by xb, right? So so here I'm just going to state that, well, the mu a comes from here in the top, and then the sigma a covariance of the xa part with itself comes from the subpart in this corresponding sigma. Of course, the corresponding precision matrix of just the xa part does not only depend on the covariance of the same part, as we will see. So what we're going to spend a bit of time on here is the conditional distribution, right? So if given a value of xb, what is the distribution of xa, right? So intuitively, this should be also Gaussian, but what does it look like? Let's first have a quick look at the geometric intuition of these marginal and conditionals, and then we go into the math, and then look at the geometry again, right? So here is the picture of what we were trying to solve, right? So in here, we see the familiar elliptical contour of the joint of xa and xb. And if we marginalize over b, basically imagine this is an elliptical sort of mountain, and then we squash the y-axis basically to nothing, basically collapse the probability mass of the screen contour into 1D, then the resulting like one-dimensional mountain that sits on one dimensions of xa should be like this blue curve. The mean is here in the center. Okay, yeah. Good to denote the mean here. And then this corresponds to the mean of 0.5. And then the overall variance is basically the overall spread of this green ellipses projected down to the x-axis. So that's pretty intuitive. And then what happens during conditioning, right? So if we know the value of xb, it's equivalent to taking a slice in this essentially three-dimensional elliptical mountain. And then we're just looking at the distribution of xa on this particular slice, so to speak, right? So geometrically, it will correspond to this red sort of more peaky distribution. So that's sort of the intuition. Let's see how we can mechanically make this happen. Another note is that from this section onwards, we're not going to be able to prove everything within the live in the workshop session. Because there's sometimes too much details. I'll pick basically parts that I think are important. You may not agree with me about the relative importance, but at least this gives you a hint about like how some of the proofs to go. And if I leave a small gap, hopefully you can fill it in. And contrasting this with some of the last year's lecture slides, you can end the book. Hopefully that's enough, right? So before we do that, let's do one more step of preparation. We kind of, in 2 slides ago, we kind of say, oh, here is the precision matrix is defined as the inverse of the covariance matrix. That was it, and we partitioned them. We haven't said what are the relations between these partitioned parts of these sub-precision matrices to those sub-covariance matrices. So the relationship is actually written at the bottom in 2.79 and 2.80. And where does this basically a mess of a matrix multiplication expressions come from? So it comes from this identity from linear algebra. Basically, if we have partition matrices, let's call each part A, B, C, and D, and we invert this matrix. Turns out that the partitioned matrix inverse can be expressed in terms of A, B, C, and D and their respective inverses. So basically, in here we pretty much assume so A and D they're square, and then they're invertible, right? And B and C are not squares. B and C are rectangular, but for one thing to note for covariance and precision matrices is that, as we said 2 slides ago, both of these are symmetric. Therefore, the subpartitions of the cross terms are transpose of each other. Same goes with the precision matrix. So we're just going to take this expression in the middle for granted. And one way to build your own intuition and also verify this. So here's the trick, the imprecise trick that I use is that I pretend these A, B, C, and D are scalars, and then I compute the inverse of this small matrix by hand to verify that this is true. So, and of course, we need to take care of like matrix multipliers and how the intuitive, like the intuitive small scalar matrix of scalars generalized to that. We'll use this trick again. In here, I leave you to do this. But what is sort of important here is there is this, if some of you might have taken the corresponding linear algebra component that talks about the short complement of the matrix. This is an important quantity, and there are books written about it. Despite that it looks like not simple, it is very useful in various matrix manipulation tasks. So here we're just going to use it as is. As you can see, that there is basically symmetry or rotational symmetry between the terms A, B, C, and D. In here, 2.76 is written in a way so that the inverse of the first submatrix essentially is a simple expression given the Schur complement, right? So if we plug in 2.76 to 2.78, we can see that basically the submatrix of the precision of the XA part is essentially the Schur complement, inverse of the Schur complement. So if we plug it in, it says like, oh, A is sigma AA, and then B inverse D times C, basically it's the cross term multiplying the inverse of B's covariance in the middle, right? Right, so it's just matrix manipulation, and that will get you to 2.80 as well. So this is how the precision and matrix and covariance are related. Now here is another useful trick for manipulating Gaussians. It's called completing the squares, or basically pull out the important parts, right? So a useful view for manipulating Gaussians is that if we have a Gaussian distribution with mu and sigma, we can basically, and we take the log of it, right? So for Gaussians is basically a bunch of constant in front. If we take the log and the exponential term cancels out, right? So these two parts will cancel out. And then we're left with the quadratic expression of x. And that's usually the important part we want to focus on. And if we remember the multivariate Gaussian expression here, the quadratic expression looks like this. Basically, what's called the Mahalanobis distance of x and mu, basically modulated. Basically, it's the inner product of x minus mu is itself modulated with the inverse of the precision matrix, or the inverse of the covariance matrix. Another trick is that if we expand this quadratic term involving matrix vectors and matrices, I see that the tutorial this week, if you have been to one, each tutorial have given the matrix cookbook as a pointer. So I guess after a while, you get familiar with some matrix operations, and expanding this inner product is one of them. So basically expands into x transpose inverse of covariance x. And then there's a linear term of x transpose precision plus and mu. Note that these products, the result of these vector matrix vector products are all scalars plus constant. This constant is basically the term mu transpose precision matrix and mu transpose and mu, right? So if we take this view, this constant at the end can essentially be grouped with the constant in the front, and they all become constants. So when we manipulate Gaussians, the constant take care of essentially normalization and make the Gaussian distribution normalized to 1 on the domain of x. So with that, we're going to essentially look at, well, take this quadratic term again, this first line we just saw in the last slide. We're going to expand it now with the partitioned covariance and precision matrices. So because like the covariance matrix appears at inverse, it's simpler to expand it with the components of the precision matrix. We basically plug in the partition, and then it expands into 4 parts, each part corresponding to, so for example, the first part is the part concerning x of A, the last part is concerning x of B only, and then there is the cross part due to the matrix vector product that basically is involving both XA and XB, right? So our goal, remember a few slides ago, is to solve, right, so my screen share is gone. Let me re-enable it. Great. Right, our goal is to solve the conditional distribution of XA given XB. In here, we're now treating XB as constants. So they're now constants with respect to XA. Our XA are the variables, XB are given. Remember the geometric intuition with X slicing on the constant value of XB. So from the last slide, the trick of completing the squares or identify essentially the quadratic form, we can see that so the quadratic term involving XA only come from the first term, right? So the quadratic term is essentially 1/2 minus 1/2 XA transpose precision matrix of AA and then XA. So from this, we, and okay, there's an intermediate step as well, which involves expanding this due to Bayes rule, P of XA given XB is P of XA, the join of XA and XB, join, divided by P of XB, right? So the expression 2.70 is the join term. And then the marginal distribution of XB come from about 3 slides ago. There was an expression about that. So that's 2.98 will give you this. And or in other words, if you recall, we said the marginal distribution basically is the respective part of mu and sigma. So we can say that basically the sum of this becomes, sum of the last term on this slide essentially becomes constants, and XB are constants. So here, the quadratic term then is only the front term. Therefore, the covariance matrix of A given B is only the precision matrix of A with itself, which is a bit curious. We can look at it a bit more later. And then the linear term here comes from 2 sources. So one source of it involves XB, basically terms such like this, XB sigma B and A times XA. And also there's linear term involving just XA, well, for example, mu of A, sigma, well, gamma, lambda of AA, and XA itself, right? And there is no linear term in the last of these 4 terms. So basically, if we collect each of these linear terms together, we will be able to arrive at 2.75. So I'm not going to do it in real time. So for now, you can say, oh, I'm asking you guys to trust me. The expression downstairs, 2.75, is the result of after collecting these terms and simplifying, right? So putting all of these manipulation results together, we get this summary of conditional distributions and marginal distributions. What is interesting here is given xb, a particular value of xb, we have, well, from the previous slide, right? So the precision matrix of AA depends on the covariance of A, and also the and then the covariance between A and B, and also the covariance matrix of B, XB. What this means is that this matrix is still symmetric and PSD, and positive semi-definite. And the intuition, again, from result in the matrix cookbook, if we have the difference of two symmetric and semi-definite matrices, then like in the two-dimensional case, ellipses, the length of the axis actually shrinks. So the intuition of this is that conditioning on XB reduces, right? So reduces in here is in a sort of high dimensional sense, variance or uncertainty, like covariance of XA, right? And furthermore, the covariance of XA conditioned on XB, this does not depend on XB, right? And then this mu term is basically a shift, okay, shift of mu A, where the shift is characterized by this term. So what does this all mean, right? So going back to our picture. So the mean of variable component A is here. Mean of component B is here, of mu of B, right? And as we just said, the covariance term is smaller than the marginal covariance of the variable A itself, which is verified by this picture. The uncertainty on the red distribution is smaller than the uncertainty of the blue distribution. And furthermore, this it says that the width of this, basically the width of this, let's say sigma square 8, does not depend on XB, which means no matter where I slice on this high dimensional ellipsoid, the remaining uncertainty is the same, which is a bit surprising but nice. So let's take a look at this shift term of A condition on B. So this last term, XB minus mu B, is basically this distance, right? XB minus mu B. And then the mean of the condition distribution is there, right? Somewhere in the middle of this slice of the ellipsoid. And if we draw this direct geometry here, so so the shift in mean, right? So this is this distance is mu of A given B minus mu of A, which should correspond to the whole product term. Basically, it says the ratio of the difference between the conditional mean, the shifting conditional mean, and the difference between the conditioning value XB and its mean mu B, the ratio is modulated by the ratio of, well, quote unquote, like matrix ratio in the matrix sense of the two precision components between, basically it's divided by the precision of A itself, and then multiply it by the precision submatrix between A and B, right? So we can think of it basically as the two sides of the triangle. So that's the intuition. Hopefully that helps. So in the beginning, we said we're going to get this in 3 steps, and we're now at the last step. So in fact, this is this part. The last part of this will be the first question of your practical part of assignment 1 in the Bayesian linear regression part. After we talked about this, hopefully that question will be relatively straightforward, right? The next step, also covered in the book, is to derive the Bayes theorem for Gaussian variables, in which then we express, rather than xa and xb, we now express things in x and y. So just to jump ahead, so p of x in here correspond to ultimately what we want of p of w, the prior of weights, and then p of y given x is the likelihood function, basically the distribution of target variable given w and also input, right? And here A is the feature matrix phi. It's not random. It's considered given. Right, and then L minus 1 is, well, we can roughly think of it as beta minus 1 that we've seen, the noise parameter. And the goal is to infer essentially P of W given target, basically the posterior. Okay, so this part does appear in the slides of last year, and it appears without the conditioning of Gaussian part. So now you know why, like, where we're going with this, hopefully. So, and 2.114 is essentially the likelihood term. So from what we talked about in the last 10 minutes, the conditioning of Gaussians, it points to the direction of, if we wanted to reason about the Bayes theorem, essentially flipping the conditions here, we'd better look at the joint distribution of x and y. And that's what we're going to do. So we define the joint distribution as of x and y with a concatenated variable, which we call z, right? And then due to Bayes theorem, right, the log likelihood of z is the sum of log likelihood of p of x, and then the log of p of y given x, right? Given, so the stuff in the green box is what we have already defined in the last slide, right? And then ax plus b, this is the regression function, right? This is what we're going to do. If we just plug these two terms in, we get the equation 2.102, which we have made use of the quadratic term, right? Basically, we expanded, we write out the inner product inside the exponent and then say everything else is a constant. And then what we do is we expand these quadratic terms and then group them, which leads to the next equation on the slide, right? So we can verify this by essentially say, oh, right now let's look at the quadratic term of x, which comes from essentially x times the precision matrix lambda and x. So that's this part, right? And then we can say, oh, what's the next? Right, there's another quadratic term of x in the conditional y in y given p of y given x. This is given by a times x transpose times L times a transpose a times x. And the sign is the same as the one below. Therefore, it's A transpose LA times X, right? So we do the same for Y. Let's say, what are the quadratic terms of Y? Then it's only appearing here. Y transpose times L times Y. So this is what we get as a quadratic term. So we can collect the linear terms like accordingly, meaning we need a different color maybe. Okay, let's see. So the linear term between X and Y only appears in the second part. So basically, if we have Y times L times AX, that will give us this linear term, right? And then notice that the two linear terms are actually transpose of each other, right? Remember when we transpose the matrix product, we just transpose each component and flip their order. And you might ask, where did mu go, right? So the mu times lambda times mu will get absorbed into the constant. And in here, because we're modeling Z, right, our ultimate goal, right, it's sort of spelled out in the next line. We want it, so the goal is to come up with the quadratic form of Z so that we can spell out the precision matrix of Z. All right, and the linear term of X in the first term above will correspond to like the linear terms in Z, which we won't look at just yet. So here's another trick. In order to arrive at the form of the precision matrix, it's helpful to sort of, at least it's helpful for me, that's how I do it, to essentially work on like a scalar, smaller version of like what happens if we do this matrix product, right? And it's not hard to just do the work and expand this as if we have, right now, basically, we have the expression upstairs and we wanted to arrive at the expression, like derive what the 2x2 matrix is, or 2x2 matrix components are. So this expands into A of X squared plus D of Y squared, right? Plus CXY plus BXY. Right, you can verify that. So what this means is the coefficient, right, where X squared in vector terms is essentially X transpose coefficient or matrix X, right? So this is roughly A, right, in this toy example, and then we can just map it that way. It's worth noting that B and C, or basically LA, or these are transpose, these are symmetric matrices, so L times A is essentially A transpose L transpose, where L is symmetric, but A is not a square or symmetric matrix. So that will give us the precision parameter of Z as 2.104. So you might say this is a bit tedious, but I would argue that if you encounter Gaussians again, you know how to deal with them. So after we have the precision parameter of Z, we can invoke the work we did in the conditional distribution of Gaussians, and then basically arrive at the following distribution. Given the joint distribution for X and Y, the conditional distribution of X given Y is as follows. So we're not going to derive the mean. We can simply verify the covariance as from 2.73, the covariance of X given Y plugging into this covariance of A given B is the inverse of the component precision matrix. And the component precision matrix here is basically here. So this is, okay. Right. So we kind of put the two parts together right now to help us arrive at what actually assignment 1 asks you to start from. So where does this lead us, right? So before we go, we just, here's the recap of the expressions that we just looked at. So this was the covariance we just worked on. And then essentially this is the posterior probability we wanted to solve. And what this allows us to do, right? So on the upper left-hand corner of this slide, I just pasted the last slide again, shrunken. And then we need to essentially plug this in and then arrive at what the book states is the posterior distribution of W given T. And we essentially need to solve for the mean and covariance matrix given n data points. So the basic way to go this is essentially a change of symbols. So going from x's w's as we say, and then y's are target variables. And then we just remember that we want, again, so y is an overloaded symbol here. Throughout the chapter, we essentially have y as the target, or the model y is something like phi transpose x, right? Where with one padded, right? So, and this is roughly correspond to ax plus b. And notice that we have the bias term absorbed into x. So essentially the bias term don't appear downstairs. So if you plug all of these in, we will have this expression of mean and covariance. Again, this 3.50 and 51 looks a bit busy. Let's build the intuition of this by looking at an informative special case. Right, so what we just covered is most of Bayes regression. So let's just talk about this special case of isotropic Gaussian priors. So now, instead of saying that the general prior, right, is P of W, is this is the general case of mu, or actually M0 and S0. We now say that M0 is the zero vector, I mean zero mean, and S0 is basically a variance, or every dimension of W has the same variance alpha. And there is no covariance because a priori we don't know how different components of W are related to each other. So that's a sensible way of modeling, right? If we don't know, we can say, well, put less constraints. So if we plug in, essentially combine these, we get the expression of the posterior distribution under isotropic prior. If we compare, so it's informative to first look at the covariance matrix. It's basically the prior covariance, right? In here, this is, or actually, this is the precision matrix. Let me be precise. So Sm minus 1 is the precision matrix. It's basically the isotropic precision, alpha times I, plus like a version of the covariance matrix scaled by the noise parameter beta. So this is interesting. It says, so imagine we like we're collecting data incrementally and estimating this. Imagine n goes from, yeah, like a few points to many, many points. Infinity. Then the first term does not change, but the second term, basically phi transpose phi, will grow as the number of data points grow. So what this means is that the precision matrix will be driven increasingly by data as we have more and more data points, which is like an informative view of Bayesian models. Basically, if we don't have a lot of data, it will be dominated by the prior. If we have more data, then the estimation result will be dominated by the data, which kind of automatically modulates the role of the prior, and that's nice. What you may say then, okay, what about the mean, right? So the mean is basically the covariance matrix times the data times the target. And this might look vaguely familiar, but let's just bear with me for a second when we can look at the next view of the Bayesian regression. And then we'll pause for questions. So okay, so we just worked through a lot of math, and here is a way to pause and look at this and see how it connects to what we already know from earlier this week. So what we claim now, log of posterior is the sum of log likelihood and log of prior. What this means is the log of posterior, basically this expression, under the isotropic Gaussian prior can be expanded into this. I'm not going to derive this, and this is essentially exercise for the manipulation of the quadratic term of Gaussians again. But it is quite common, and we can also derive this from Bayes' theorem. So there are two sources of deriving this. I would argue that Bayes' theorem way, or the product rule way, is easier than essentially the quadratic term form of Gaussians. Of the expression in the last page. So we can derive it two ways, and then we basically have the log posterior is basically a weighted sum of the square error and also the regularizer. That's quite interesting because what we just stated was, we wanted to have the maximum posterior solution, and then now this expression is essentially the same as the regularized linear, like regression model from either earlier this week or Friday last week. So things connect again. Moreover, we claim that the maximum posterior estimator of W actually has a correspondence with the regularized maximum likelihood solution, right? And it should be because of the connection of the loss function upstairs. So if we just plug in the expression of S of n inverse under isotropic prior into the mean expression, we get essentially this expression downstairs. So to see this, we essentially do beta times alpha I plus beta phi transpose phi transpose t. Right. So now it's easy to see that we have like inverse. So if we take beta inside, then this gives us essentially alpha over right, so if we divide beta in the inside term of beta over I plus phi transpose phi inverse phi transpose t. For W, we mainly care about the direction, and the magnitude matters much less. In this case, the magnitude mainly influences the regularizer term. Yeah, so we can see that, well, we get the normal equation back again. Right, so familiar things appear again. In the assignment, you're asked to essentially use these to reproduce this pictorial view of Bayesian linear regression, which I think is a nice way to wrap up this rather technical session. So if we put a broad prior, as in this picture, this is basically, yeah, alpha or 0 and alpha minus 1, right? The prior looked like this, and if we observe one data point, we can see that it serves to essentially, it shrinks the posterior by a lot. So this will be essentially, we're plotting M1 and S1 here. And then if we observe two data points, we are plotting N of W or M2, S2 here. We can see that having two data points narrows down the hypothesis by a lot. And if we use this to essentially sample W, we can see that which correspond to sampled lines in the data space. We can see, first of all, at first the lines are quite random, and then after observing one data point, the lines are still quite random. After two data points, they start to define a line, and there is a clear trend there. After three, or actually not three, in here, after a couple of more data points, the lines, the sampled W's, the W's are quite concentrated in a wave space. After n data points. And also the lines are quite concentrated, well, if we visualize in data space. So all of these visualization code are provided to you. So if you have implemented the posterior distribution properly, you should see something like this with the proper choice of priors. Right, so what we have covered is Bayesian regression. I know we're at the hour, so feel free to leave if you are like signed up for the 1 p.m. in-person lab. Otherwise, we're going to talk a bit more about predictive distributions, which is a nice Bayesian tool to reason about the models we learned. So Bayes' rule again. So one can argue that the goal of estimating a regression model is more of estimating basically the value of the function at some unobserved value of x than to reason about or the weight vector itself, right? In fact, there is a cultural divide between statistics or social science and, say, the typical applications of machine learning. If you are going to use Bayesian linear regression for, let's say, social science, then you would want to reason about, let's say, what are the significant factors, right? Reason about W. It happens a lot in economics and other areas, but somehow culturally in machine learning, one would also want to learn on pi of the data and then predict on unobserved value of x. So I would say both goals are valid. So we're going to address this forecasting goal. And we invoke the Bayes rule again. So we wanted to quantify the uncertainty of the forecasted variable y, right? Why do we want, so if we don't want to forecast uncertainty, we will simply say that, okay, y of x w is simply phi transpose phi of x, yeah, times w, or the other one, the inner product of the weight and the feature, and we're done. But in a lot of cases, we want to be like not just say what the mean is, but also how uncertain we are. And Bayesian linear regression gives a language and tools to say this. So this is basically Bayesian Bayes rule again, except we're integrating over W. So a pictorial view of this will be, remember the familiar picture, I remember it's figure 1.16, basically for a regression function y at each given input x, we are looking at a little Gaussian distribution around the model mean, right? In this expression 3.57, we're just basically looking at, and then each of these red curves regression function y correspond to one particular value of w, and now we're just looking at different w's, basically different version of these pictures for different w's, and then averaging them out, right? And the averaging is done using two parts. One part is the distribution of target given the model, which is nothing new. We saw this twice already, which is depicted in a picture, this little blue distribution. And the second part is the posterior distribution that we've been working with in this lecture. Which is another Gaussian parameterized by mean after seeing endpoints and also the covariance. And it's driven by the underlying prior distribution we specify for W parameterized by alpha. Right. So take these two parts, plug them into the marginal distribution, or one of the results in earlier in this lecture. We essentially get back, I won't go through this, so you can say, well, trust the book and trust me for now, it's going to be another Gaussian. And the mean and covariance, because we're looking at one-dimensional uncertainty for the target value here, is like 1 over beta, the noise uncertainty, the noise magnitude, plus essentially the inner product of the input vector modulated by the current posterior precision matrix. So this makes intuitive sense because we already said that the noise cannot be, like the noise of P of t given W, and it cannot be reduced, right? So the uncertainty at any point is at least 1 over beta. And then it's related to the current posterior of estimate of W and also the input. So here's the pictorial view about this. As we can see, the pink cloud, or the pink region, denotes the uncertainty. So note that in here, the mean of the predictive distribution is the mean of posterior times the current data point. So it's a function of x. So we're looking at the familiar sinusoid example again. There, we can see that as we observe more and more data points, so this should be read in conjunction with the last set of plots, the predictive mean sort of approximates the true function, which is sinusoid. With 1 or 2 data points, it's really not great. But with 4 data points spread over the space, it's starting to show the sinusoid shape and so on. And then what's worth noting is that the uncertainty or the predictive variance is also a function of x. You might think eyeballing the last plot, the predictive variance may be pretty close to 1 over beta, but if we have less data points, it actually quantifies at the x values where we have data points, the variance or predictive uncertainty is smaller, but in between these observed points, the uncertainty is big, right? So this is quite intuitive and nice. It gives us a rich language to express this. Again, if you will be looking into Gaussian processes or, in kernel machines, this is a useful view. So we can also sample, essentially sample the weights W from this posterior, feed it into the set of basis functions, and it also shows us, like in this data, in terms of the sampled regression functions, what it looks like. So this is basically figure 3.9 is the kernel view of this like direct linear regression that we were looking at. Right. Okay, the last block of content, which I know we have gone through a lot. So is there any questions so far? Nope.
Yes.
Oh, yes, please.
Could you please explain what is alpha is in the previous slide?
Yeah, sure. Here, this alpha, right? This
yes.
Alpha is the precision parameter for the prior of W. So it's so it comes from the slide where we say isotropic Gaussian priors. So we first started with a generic prior with mean and covariance, and then we say we assume each dimension of W behave the same, and their precision is alpha, or variance is alpha, like 1 over alpha. So that's alpha.
Okay, my next question is how that's different from the beta, because beta is also precision, right?
Yes, beta is the precision parameter of this guy, basically of the target variable given the input and the regression function. Right, so beta is the precision parameter for the likelihood, as Namas said that. But alpha is the precision parameter of the prior. Hope that helps. So I'm just going to write it here.
Yes, thank you.
Yeah. Okay. So yes, there is a number of quantities sort of keep track, and it can be hard to keep track of them all at the same time in your head in real time, especially if you are hearing this more or less for the first time. I would just say, just keep at it and it will get better. And I guess you're not required to do this in real time. You're always allowed to look up different expressions anyway.
And I'm sorry.
Yeah, go for it.
Is that alpha I, the I stand for identity matrix?
Yes, that's correct. It's an identity matrix in the same dimensionality as wave vector W.
Yeah, thank you.
Yep, great. So for those of you who have dealt with data in one way or the other, statistics or databases, you would probably have heard about the expression curse of dimensionality. So the next 2 slides are going to basically tell you what it means more precisely, especially for Gaussians. There is a surprising result. So in a nutshell, the reason we care about this is that we've basically been dealing with calculus and linear algebra on probability so far. And using linear algebra as a tool allows us to operate in this n-dimensional space that we can't even visualize and essentially operated as the same way as a low-dimensional space. But the phenomenon of cursive dimensionality basically says that some of the intuitions we have in 2 or 3 dimensions, it no longer applies if n is large, right? So the reason for this are a couple of folds. So here are 2 examples. One is from the discrete space. For those of you who know what KD tree is and what database is dealing with, you would have seen this. For others, let's just look at this simple example. If we partition space into essentially discrete cells, right, and we consider how many neighbors each cell have in each different number of dimensionalities. So, for example, if we consider immediate neighbors in 1 dimensions, like number of neighbors, there's 2, right, in 1 dimensions. In 2 dimensions, let's say there's 4. In 3 dimensions, there is 8, right? So in d dimensions, there's 2 to the d number of neighbors, and this grows exponentially. So for those of us in computer science, we know that, like for example, in KD trees, you need to check the cell and check all the neighboring cells. If there's exponential number of neighbors, that's bad. And in continuous space, so here's another example. If we have a sphere, unit sphere of radius r equals to 1, we want to know what fraction of the volume of the sphere lies between r equals 1 and r equals 1 minus epsilon. So this is essentially a thin shell, like epsilon is usually small, at the surface of the, like on the surface of the sphere, right? Right, so let's say epsilon is small. So the way to reason about this is that volumes scale polynomially, like, or say basically it scales like r raised to the power of d, right? With the d is the order of the polynomial. And then there's some constant in front. For the purpose of this discussion, we don't really care about what the constant is because we're going to look at the fraction of the volume, right? This expression downstairs is exactly what spells out the words upstairs. The fraction of the volume, well, the volume of the whole sphere is v of d 1, right? The fraction of the volume on the thin shell is v of d at r equals to 1 minus v of d at r equals 1 minus epsilon. And well, we all know polynomials. It's basically the difference between 1 and this polynomial term. So we can see that, well, yes, epsilon is small. We want to, like, say, take a cut here, somewhere 0.1-ish. And we basically plot these polynomial curve for different orders of d. For d equals to 1, so there is no surprises. This is basically, this curve is epsilon. We can see that these are curves that sort of bend. They sit above d equals to 1 and bend downwards, right? And for large number of d, right? So 20 is not even that large as far as vector spaces are concerned. For small number of epsilon, basically almost all of the volume is sitting on the thin shell and nothing at the inside of the sphere, so to speak. Right. So that's very counterintuitive. If we look at a ball, which are supposedly filled with mass, but almost all of the weight is sitting on the surface of the ball, but not inside the ball. Right, so it's like we have a beach ball, which we thought was solid, but it's actually an inflated beach ball where all of the mass was on the shell. This is quite counterintuitive. So what does it mean for probability distributions, right? So what does it mean for Gaussians then? So if we look at spherical Gaussians, which are not quite balls, there's one more considerations here. We know that even in multidimensional Gaussians, the probability density function is the maximum at the origin, right? So we can see on this red curve is basically half of the Gaussian. We can say extend the red curve, and this is what the Gaussian looks like, and the density is the largest at 0. Even if we have two-dimensional Gaussians, drawn green, we still have the, let's say we do two-dimensional isotropic Gaussians, we still have this contour lines where this probability mountain are still highest at the mean, right? So the surprising result is you will say, why does, for two-dimensional Gaussians, the probability density with respect to radius of the Gaussian has 0 at the mode of the distribution, which is rather counterintuitive, right? So I'm going to give a hand-wavy explanation, which is using this volume of sphere argument that we just derived and the Gaussians. Basically, the probability density with respect to radius r is the product of the PDF function and the relative volume of the spheres, right? Therefore, if the relative volume of the spheres at the origin is 0, it's going to go to 0. The more formal argument goes involves the derivation. The general direction you go is as follows. Assume we're in 2 dimensions. Then we do a change of variable into the polar coordinate involving r and phi, where r is the radius and phi is the angle. And then we rewrite the expression of Gaussian densities in 2 dimensions with respect to r and phi. We essentially get expression that does not depend on phi. Well, it's not super surprising because it's isotropic. Doesn't matter which angle we look. And then we integrate out phi. Basically, we get an expression involving just r times x of r squares. So it's easy to verify that this is 0 at the origin. So it's surprising, but it's a mathematical artifact. So it gets worse if we move to higher dimensions. Basically, for high-dimensional Gaussians, the density is again concentrated around a thin shell that is away from the origin or the mean, which is rather counterintuitive. So this is the bit on cursive dimensionality. We would like to conclude this section on regression by discussing like what we learned on basis functions, right? In this section, we have committed to basically, we have observation x, we add 1 to it, right? And then we transform it to phi of x, right? And these are fixed basis functions. It leads to a range of useful properties. We basically now have closed form solutions of the regression problem involving this basis vector, least squares functions. We also have tractable Bayesian treatment. It's a little bit involved in matrix algebra, but it is tractable and very computable. You can readily implement in code, as you will see in the assignment. And then for suitable choice of basis functions, we can model any regression function, which is nice, right? So arbitrary nonlinearities is the focus. So despite looking simple, the linear regression model for regression is quite powerful. The downside is that the basis function cannot adapt to data, right? And when the dimensionality D is high, then the basis functions needs to grow exponentially. So that is bad. So the subsequent chapters will cover two fixes. One is localized basis functions that only live in regions where there's data, such as SVM, RBF networks. And then there is ways to adapt the basis function, such as using neural networks, right? And then, okay. So that concludes our linear models for regression section. Are there any questions so far? Nope. Given that we're at time, I'm just going to stop the recording.